Hello my dear students, today we are going to study computer organization and architecture subjects and the topics will be adders and subtractor. My name is Himanshi Chaudhary. I am from Computer Science and Engineering Department. Let's get started. First of all, we will see the content that we are going to study. So our content is half adder, full adder, half subtractor and full subtractor. These all digital circuits are categorized under combinational circuit. Now to design combinational circuits, we must know the gates. So the first gate is AND gate. AND gate is having two inputs and one output. And the symbol for AND gate is this, the type. Now the truth table for the AND gate is, if there are two inputs, the possible inputs will be this 0, 0, 0, 1, 1, 0 and 1, 1. The output for the AND gate is, if both inputs are low, that is 0, then the output will be low, that is 0. If the inputs will be 0, 1, output will be 0. If the inputs will be 1, 0, then the output will be 0. When the inputs will be high, that is 1, the output will be 1. Now you can conclude that if only both the inputs are high, then only the output will be high, that is 1. Let's see the next gate. The next gate is OR gate. OR gate is having two inputs, one output, and the symbol for OR gate is this. The truth table for OR gate is this. In this there are two inputs. These are the possible inputs. And the output for these possible inputs is this, that is 0, 0. If 0, 0 is input, then the output is 0. If 0, 1 is input, then output is 1. If 1, 0 is input, then output is 1. If 1, 1 is input, then output is 0. Now you can see in OR gate, if there is at least one input is high, then the output is high. If both the input are low, then only the output is low. Now let's see the next gate, that is XOR gate or exclusive gate. The symbol for exclusive OR gate is this. There will be two inputs and one output. Again, we will see the truth table. For two inputs, these are the four possible inputs and this is the output. For 0, 0 it is 0, for 0, 1 it is 1, for 1, 0 it is 1, for 1, 1 it is 1. Now you can conclude that if only one of the input is 1, then only the output is 1, else the output is 0. It means that if both inputs are equal, then the output is low. If both inputs are different, then the output is high. This is exclusive OR gate. Now let's see the combinational circuit definition. So the definition of combinational circuit is, the combinational circuit is a connected arrangement of logic gates with a set of inputs and output. It means with the help of logic gates, some inputs and outputs are connected and they will give some desired output. Now to design the combinational circuit, following procedure is involved. It means there is a predefined procedure to design a combinational circuit. To design combinational circuit, first of all we must define the problem statement. So the problem is stated, then input and output variables are assigned letter symbols. It means first of all we must know the count of input and output, then letter symbols are assigned to inputs and outputs. Next is truth table is defined for these inputs and outputs. A relationship is defined for these inputs and output and that table will be known as truth table. Now with the help of this truth table, Boolean functions are obtained for each output. If there are two outputs, then for two outputs Boolean functions are obtained with the help of this truth table. Now after knowing the Boolean function for each output, logic diagram is drawn. So this is the procedure to be followed for any combinational circuit. Now let's move to the first combinational circuit, that is half adder. So our first combinational circuit is half adder. So to design this combinational circuit half adder, first procedure to design half adder is the problem is stated. It means that you must write the problem statement. So the problem statement for the combinational circuit is a combinational circuit that performs the arithmetic addition of two bits is called half adder. It means the combinational circuit which can add two bits is called half adder. Next step to design combinational circuit is to know the input and output variables are assigned letter symbol. It means you must know the count of input and the count of output to design this combinational circuit. Now it is defined that the number of input in this half adder will be 2. But what about the output variables? To understand the count of output variable, I will take one example, that is 19 plus 3. As you know, 9 plus 3 is 12. So from this 12, 2 is written over here always as sum. So this is sum. And this one is carry. So carry is written here. Now this one and this one are added and the result is added here. So the answer is 22. So whenever there is the addition of two bits, there could be two outputs, that is sum and carry. So here we have written two inputs and two outputs and we have named them as XY and carry and sum. The block diagram for this combinational circuit will be like this. This is the black box in which we do not know the circuit, this one, and this is input and this is other input and this is output and this is other output. So the next step is to make truth table between input and outputs. So these are the four possible inputs for the two inputs. Now we must know that what will be the carry and what will be the sum for these possible inputs. Let's understand. Whenever 0 plus 0 is added, the sum will be 0. So is there any carry for this? No. So carry will be 0. Now when 0 plus 1 is done, the sum will be 1. But there is no carry, so carry will be 0. When 1 plus 0 is done, then sum will be 1, but there is no carry. But in the case of 1 and 1, what will be the output? These are bits. These bits, when converted to normal numerical value, it is 1 plus 1, which results 2. So these are bits and these are numerical value. This 2 in binary is written as 1 0. So when 1 plus 1 as bit are added, the result will be 1 0, where 0 is the sum and 1 will be carry. Let's see the table. So you can tally that this is the table for carry and sum. Now next step, by looking this truth table, we need to design the Boolean functions for each output. So let's design. To design the Boolean function, we need to see that where is 1. So for sum, here is 1. So for carry, the Boolean expression will be x dot y. So for carry, the output expression will be x dot y. Now we need to calculate the Boolean expression for sum. So across 1, the inputs will be seen and the output expression is generated. For this one, the input expression is x bar y, plus for this one, the input expression will be x y bar. So the Boolean expression for sum will be x bar y plus x y bar. This is a simple statement for x XOR y. Now from this truth table we are having Boolean expression. With the help of this Boolean expression we can design the logic diagram for this half adder. So next step is to draw logic diagram. So let's draw this. For this sum, the logic diagram will be, here we are writing sum, x and y are the inputs and the XOR symbol is drawn here. So this is x XOR y. So sum is generated. Now we need to design x dot y. So x or y is already here. We need to put AND gate only. So we will draw this. So x and y is taken from here and the AND gate is put here and the output generated is x dot y, that is carry. So this is half adder. In half adder you need to add 2 bits and the outputs will be carry and sum. First we will draw the truth table, then we will produce the Boolean expressions, then with the help of Boolean expression logic diagram is drawn. This is to design the combinational circuit half adder. So my next topic is full adder. Let's see the definition or problem statement for the full adder. A full adder is a combinational circuit that forms the arithmetic sum of 3 input bits. It means full adder can add 3 input bits together. So it simply means that the number of inputs will be 3 and the number of output will be 2, that is sum and carry. Now this is the block diagram for the full adder where x, y, z are the inputs and sum and carry are the outputs, and this is the black box where we do not know that what the design inside, that we need to design with the help of truth table, and we will then produce the Boolean functions and then we will produce or design the logic diagram for the full adder. Now let's see the truth table for the full adder. The inputs are x, y and z and the outputs are carry and sum. When the number of inputs are 3, the truth table for this or the possible inputs are these. Now we need to evaluate the carry and sum for these inputs. So let's evaluate. When 0 plus 0 plus 0 is done, sum will be 0 and there will be no carry. So carry will be 0. When 0 plus 0 is done, it is 0 and 0 plus 1 is always 1. So there is no carry. So the output will be 0 for carry. 0 plus 1 is 1. 1 plus 0 is 1. So the sum is 1 and carry is 0. Now 0 plus 1 is 1 and 1 plus 1 is 2. So the digital value for 2 is 1 0, where 0 is sum and 1 is carry. Next 1 plus 0 is 1 and 1 plus 0 is 1. So the sum will be 1 and carry will be 0. Next 1 plus 0 is 1 and 1 plus 1 is 2. And the digital value for 2 is 1 0, where 0 is sum and carry is 1. Next 1 plus 1 is 2 and 2's digital value is 1 0, and then in 1 0 0 is added, then the answer will be 1 0 only, then 0 will be the sum and 1 will be the carry. Now 1 plus 1 is 2 and 2 plus 1 is 3 and the digital value for 3 is 1 1. So 1 will be the sum and other one will be the carry. Let's see the table. You can tally the inputs and outputs. Let me clear this annotation. Now with the help of this truth table, we can design the Boolean expressions. Now you must know the Boolean expressions are evaluated across these ones. Now if this is 1, then it will be x bar dot y dot z plus the next one. So we will see that what will be the Boolean expressions for this full adder. The evaluated values are carry is x dot y plus x XOR y dot z, and the sum is x XOR y plus z. But you must know the derivation, that how these values are derived. So let's move to that portion. This is the table for full adder. Now first carry is evaluated. Along 1, the number of inputs are written like this. This is x bar y z. X bar y z is written over here. Now next one is taken for carry. Here is next one. It will be x y bar z. X y bar z. Along next one it will be x y z bar. X y z bar. And along next one it will be x y z. So this Boolean expression is generated with the help of this truth table. Now we need to reduce this. So from these two Boolean expressions, z is taken the common output. So it will be x bar y plus x y bar. It is written over here. And from these two Boolean expressions, xy is taken common, and then it will be z bar plus z. Z bar plus z. Now you must know, if any Boolean value is added with its complement, then this results to 1. So this value will be 1. It means that xy dot 1 is here. So it will be xy only. And coming here, observe this x bar y plus xy bar. This is simply can written as x XOR y. So the reduced Boolean expression will be z dot x XOR y plus xy. So this will be the expression for the carry. Let's see the Boolean expression for the sum. This is the truth table for sum. So for everyone we need to write these inputs like this only. So we will write, for this one it will be x bar y bar z. X bar y bar z is written over here. For this one it will be written x bar y z bar, x bar y z bar. Then across this one it will be x y bar z bar. It is written over here, x y bar z bar plus the value across this one, it will be x y z. Now this will be the Boolean function for the sum evaluated with the help of this truth table. Now we need to reduce this. From these two Boolean expression, we have taken x bar common. Then it will be y bar z plus y z bar. It is written over here. Plus from these two, x is taken common. Then it will be x bar z bar plus y z. Now closely observe this statement. It is simply similar to a bar b plus a b bar. Here a is x and b is y bar z plus y z bar. Okay. Now this is b and this is b bar. You must evaluate it. So if the complement of this Boolean expression is taken, the output will be this only. So this statement is very much similar to like this statement. It means a bar b plus a b bar. It means it can be written as x XOR y XOR z. Y XOR z because this is b, and this statement can be written as y XOR b. So the value of sum will be x XOR y XOR z. Now we are having Boolean expressions for carry and sum. Let's design the logic diagram for the same. Now we will design the logic diagram for the full adder. We are having the expressions over here. Carry is x dot y plus y, x XOR y in bracket dot z, and the sum is x XOR y XOR z. So this is the logic diagram for the sum x XOR y, and that is XORed with z. So here sum will be x XOR y XOR z. Then next carry. This is x, this is y. These both are applied to the AND gate, and the output will be x dot y. Now here the output is x XOR y. So here the output will be x XOR y dot z, because the second input is z. Now these both outputs are then added. So the output will be x dot y plus x XOR y dot z. So the carry will be evaluated in this logic diagram. So this was full adder where we can add 3 inputs and we can produce the sum and carry. Next we are having half subtractor. So the problem statement, the half subtractor is a combinational circuit which is used to perform subtraction of 2 bits. It means half subtractor is allowed to subtract 1 bit from another bit. One of the bit is said to be minend and other bit is said to be subtrahend. Next we must know the number of input and number of output. So the number of inputs are 2, that is x and y, and the number of output will be 2, that is difference and borrow. For this let's take one example. 31 minus 19. Okay. So when we want to subtract 19 from 31, now this one cannot subtract 9. A borrow has to be taken. So what we can do, we can give 1 from this. So this 1 will be here and this portion will be 11 minus 9 and the result will be 2. But at this side we must tell that we have taken a borrow. Okay. Now 1 has been taken as borrow from this side. Okay. Now what we can do, either subtract 1 from this 3 or add 1 to this side. There are 2 options to execute. Now if, I'll write or over here, if from 3 minus 1 we are doing minus 1, if we are picking it, then it will be 2 minus 1 and the answer will be 1. Okay. If we are picking this, then it will be 3 minus 2 and the resultant will be same, that is 1. So the output here will be 1. So here we learned that if we are taking borrow from the previous bit or number, then we have to inform this side. That's why we are having 2 output, that is difference and borrow. So let's complete the truth table. Let's subtract 0 from 0. So if 0 minus 0, then difference will be 0 and there will be no borrow taken. No borrow taken, it simply means 0 will be the borrow. Now if you want to subtract 1 from 0, then what will be the output? Let's see. But we'll move to next. Till then 1 minus 0 is 1. So difference will be 1 and borrow is not taken. 1 minus 1 is 0 and here also we have not taken any borrow. So this is the special case. Here we want to subtract 1 from 0. This is not possible. So here we will take 1 borrow. This borrow will be taken. Okay. And then this 1 0 numerically it is 2 and 1 numerically is 1. 2 minus 1 is 1 and in binary 1 is represented as 1. So the difference is 1 and the borrow will be 1 because here you have taken 1 as the borrow. So let's see the truth table. So you can tally the outputs. Okay. So wherever we need borrow, we have to write 1 over here, and here we will write difference. So now with the help of truth table, we can design the Boolean functions. This will be the Boolean function. Let's see how these are generated. See for the difference. The output is 0, 1, 1, 0. So the output is high when one of the inputs are high. So for what this input and output relationship was? It was for XOR. So it's very simple that X XOR Y produces difference. Okay. Next is borrow. So corresponding 1, there is only 1. So corresponding to this one, it is simple X bar dot Y. So it is written over here. So very simply we got to know that what are the Boolean functions for this difference and borrow. So this is the logic diagram for half subtractor, where difference is X XOR Y. So for X XOR Y, we have applied two inputs X and Y. XOR gate is designed here and difference is produced then. Next is borrow. So for borrow, I want X bar. So X is input here, and to this I have applied a NOT gate. It will convert this X to X bar. So here output is X bar and dot. Dot means AND gate, and after that Y is applied. So Y. So the outputs will be X bar dot Y for borrow. So this is the very simple half subtractor definition. Now our next topic is full subtractor. The problem statement: the full subtractor is a combinational circuit which is used to perform subtraction of 3 input bits. It means it does the subtraction of 3 input bits. What are these input bits? Minend, subtrahend and borrow input. And the outputs will be difference and borrow out. This is the truth table for the full subtractor. But first of all, we must learn that how these outputs are produced. So let's move to that. This is the empty truth table with the number of inputs and the outputs. If there are 3 inputs, the possible inputs are these. Now let's evaluate the difference and borrow out. So first of all, we will understand what is borrow input. If there is borrow input, that subtraction is saying that already there is a borrow input available. Okay, when the bin is 0, there will be no borrow input, and if the borrow input is 1, there will be borrow available. Now still, if you need borrow for that subtraction, then we will write 1 for the borrow out, and if you don't need any extra borrow, then we will write 0. So now let's understand that how this subtraction will occur. So first statement saying that 0 minus 0 and there is no borrow. It simply means this, that you have to subtract 0 from 0 and then you need to produce the difference. There is no borrow, so there is no borrow input, and the difference is 0 minus 0 is always 0, and if you have not taken any borrow for this subtraction, then borrow output will be 0. So when you need to subtract 0 from 0 and there is borrow, though you must remember that you are having 2 options for this. Either you can subtract 1 from the upper number, or you can add 1 to the lower number. Okay, we will go for this one. We are not going for this one. It means if we want to perform 0 minus 0, we will be adding 1 to this 0. So this equation will be changed to 0 minus 1 because we have added 1 to 0. So this equation will be 0 minus 1. Now for second line we are doing this. So now for this equation we must have a borrow because 0 cannot subtract 1. So we'll be taking 1 borrow. So this number will be 1 0. So for this we have taken borrow, and if we have taken borrow then 1 will be written over here in borrow out place, and this number will be 1 0 after taking borrow. Now this 1 0 numerically is 2 and 2 minus 1 is 1. So the difference will be 1. So now we are having difference 1. Next is 0 minus 1, and there is no borrow input. In this case there is no borrow input. So 0 minus 1 again is not possible. You have to take borrow. If you are taking borrow you will write 1 over here. Now again this value is 2 and 2 minus 1 is 1. So you will write difference 1. Okay. Now we are reading this. Again it is 0 minus 1. But here we are having borrow input. If we are having borrow input, I can either subtract 1 from this or add 1 to this. So we are doing add 1 to this. If 1 is added to this place, so 1 plus 1 is 2. So it will be 1 0 because we are doing it in binary form. Okay. Now 0 cannot subtract this 1 0. So for this we need to have a borrow. So 1 is taken borrow. If 1 is taken borrow, then you have to write 1 over here, and here 1 0 minus 1 0 will be 0. So difference will be 0. Next is very simple. Here we need to subtract 0 from 1. So the difference will be 1, and borrow input is 1. There is no need to take borrow out, B out. This B out is 1 only when we need to take extra borrow. Okay. Next is 1 minus 0. 1 minus 0. But here we are having borrow input. If we are having borrow input, we have chosen this. So this, in this 0 we have to add 1. So this 0 will be 1. Now 1 minus 1 will be 0. 1 minus 1 will be 0. There is no borrow taken, so borrow will be 0. Next is 1 minus 1. This one, 1 minus 1. So 1 minus 1 is 0. This will be 0, and there is no extra borrow taken, so this value will be 0 also. Now we will move to next 1 minus 1. This is the case 1 minus 1, but we are having 1 over here. If we are having 1 over here, we will add 1 to this place. So this will be 1. 1 plus 1 is 2. 2 is written like this. So this scenario is saying that 1 minus 1 0. This is not possible, so we have to take extra borrow. Extra borrow is taken. If extra borrow is taken, you need to write 1 over here, and 1 1 is 3 in numerical, and 1 0 is 2. 3 minus 2 is 1, and in digital form 1 is written like 1. So the difference is 1. Our truth table is ready. Let's see the output. Now you can tally these all. Now we are having full truth table. After having truth table, we need to design Boolean function by using this truth table. So the first, along this first one, it will be x bar, y bar, b in. Along next one, it will be x bar, y, b in bar. So it is written over here. Along this next one, it will be x, y bar, b in bar. So it is written over here. Next one, it is x, y, b in bar. So it is written over here. Now we need to reduce this. Now to reduce this Boolean expression, we will take extra from these two x bar is taken extra from these two. So the left one is, when x bar is taken common, it will be y bar b in plus y b in bar. So it is written over here. From these two, x is taken common, y bar b in bar is left and y b in is left over here. Now if you will see this, this is very much similar to full adder expression, or you can say a bar b plus a b bar. If you will check, the complement of this is this. So we can write this statement as this: x XOR y XOR b in. Next we need to evaluate the borrow. So this is borrow out. For this borrow out, we are evaluating the Boolean expression. Along this one, it is x bar y bar b in, x bar y bar b in. Then adding, along this one it will be x bar y b in bar, x bar y b in bar, plus along this next one it will be x bar y b in, x bar y b in, plus along this one it will be x y b in, and it is written over here. Now we need to reduce this. In the next statement, we have taken b in common from this first Boolean expression and the last Boolean expression. So the after taking common, it will be x bar y bar, that is written over here, plus xy. So xy is written over here. From these two, x bar y is taken common, and after that b in bar plus b in is left, that is written over here. Now you can see that this is similar to a bar plus a. Okay, so this value is 1. So what is left over here? X bar b. And this statement is the complement of x bar y plus x y bar, that is x XOR y. So this is the complement of x XOR y. So we will write this. This statement is reduced to b in x XOR y ka complement plus x XOR y. So these are the reduced steps for the difference and borrow. So after evaluating this truth table, our output for the difference and borrow is this. Now by using this Boolean expression, we can design the logic circuit. So the logic circuit will be this. Difference is x XOR y XOR b in. So difference is here, it is x, y given to XOR, and that output is XORed with b input. So difference is x XOR y XOR b in. For b out, complement of x XOR y. So x XOR y is produced here. To make complement, we must apply it through the NOT gate. Okay, then it is AND with b in. So b in input is here and it is applied to AND gate. So here we are having x XOR y complement and b in, and these are AND. So this expression is generated over here. Then we want x bar dot y. So x is here. This will produce x bar, and dot, for dot we are having AND gate, and for y we are having this line. So this will be x bar y, and this will go as input for the OR gate because we need to add these two Boolean expressions. So here we are having x XOR y complement dot b, and here we are having x XOR dot y. So b out is generated. This logic diagram is implemented with the help of Boolean expressions produced with the help of this truth table. This was the last in combinational circuit. Now I thank you all to see this video.